Hello everyone and welcome to EPulse Academy. In today's episode, we are diving deeper into the foundations of electrical and electronics engineering. In this video, we'll be covering electrical potential, electric field, electrical current, electrical materials, and finally, we'll talk about electrical mechanical analogies. With that being said, let's get started. What is electrical potential? Now, electrical potential is a measure of electrical energy. More specifically, it represents the amount of energy required to move one unit of electrical charge from one point to another. It is also known as voltage or electromotive force and is measured in volts. It has a very important relationship with electrical charge, which is measured in coulombs, and energy, which is measured in joules. And the relationship is that 1 volt equals 1 joule per coulomb. That means if it takes 1 joule of energy to move 1 coulomb of charge, the potential difference is 1 volt. Therefore, voltage is essentially energy per unit charge. Now, here is a very important point. Voltage is a differential quantity. That means voltage is always measured between 2 points. There is no such thing as absolute voltage at a single point, but voltage always involves comparison. However, in circuit analysis, we usually measure voltage with respect to a reference point called ground. For example, the node voltage at point A with respect to ground equals 10 volts and at point B equals 5 volts, and the voltage between point A and B, which we call VAB, is voltage at point A minus voltage at point B, which gives us 5 volts. So voltage between 2 points simply tells us the energy difference between those points. Always remember that voltage equals the difference in potential. Next, let's talk about the electric field. Now, an electric field is a region where a charged particle experiences a force. It points from positive to negative charge, meaning from a higher potential to a lower potential. A positive charge naturally moves in the direction of electric field, which is towards the negative charge. Now the units of electric field is measured in newtons per coulomb or volts per meter. Now mathematically, the electric field is defined as the negative gradient of the electric potential. That simply means that electric field describes how quickly voltage changes in space and that it points in the direction where potential decreases more rapidly. The cool fact is that electrical energy is stored in electric field, and this unique property helps us understand how a capacitor functions. Now let's move on to electrical current. Electrical current is the flow of positive charge through a conductor. In this case, voltage acts as the driving force that pushes charge to move. Current is measured in amperes, and 1 ampere equals 1 coulomb per second. That means current is the rate at which charge flows. So if 1 coulomb of charge passes through a wire every second, the current is 1 ampere. Current naturally flows from higher potential to lower potential. This behavior is similar to other systems like fluid flows from high pressure to low pressure and heat flows from high temperature to low temperature. Therefore, voltage pushes current just like pressure pushes water. Now here is something interesting. We say that current is the flow of positive charge, but in reality, in most conductors, current is due to the flow of negatively charged electrons. Electrons actually move from low potential to high potential, which is the opposite direction of conventional current. So why do we still use conventional current direction? because a flow of negative charge in one direction is equivalent to a flow of positive charge in the opposite direction. For simplicity and historical reasons, engineers still analyze circuits using conventional current direction from high potential to low potential. So remember, electrons move in one way, while conventional current flows in the opposite way, but circuit analysis still works perfectly. Electrical current flows more easily in some materials than in others. Materials where current flows easily are called conductors, and materials that resist current flow are called insulators. In conductors, they have free valence electrons, and these electrons can move freely between atoms, resulting to flow of electric current. Examples of good conductors include copper, aluminium, gold, and silver. Now, in insulators, the valence band is full and electrons cannot move freely. Thus, current does not flow easily. That's why materials like rubber and plastic are used to insulate wires. Finally, let's talk about electrical-mechanical analogies. Electrical systems behave in ways that are similar to other physical systems. For example, electrical systems are comparable to fluid systems and thermal systems. In fluid systems, voltage acts like pressure, current is like the flow rate of water, and resistance is like the narrow pipe restricting the flow of water. Similarly, in thermal systems, heat flows due to temperature difference, just like current flows due to voltage difference. These analogies help engineers to understand complex electrical systems by comparing them to everyday physical systems, and that's why understanding fundamentals is so powerful. If this has helped you understand electrical fundamentals in a better way, give this video a thumbs up and drop down your valuable comment below. Don't forget to subscribe because I would love to see you in the next episode. Stay curious and keep learning.